a milestone for you. I'm so glad that you are going to graduate. And then you're going to start looking for a job, right? So good luck with all of that, and let us know what you know, what help you need from us. Okay, great. So anyone else that I missed? Anyone? Please just unmute yourself and talk. Okay, great. Okay, so let's get started. Today we are great to have Charles introducing topic modeling. Now, in deep learning, in the sense of deep learning, many of you probably have learned about some type of topic modeling using the classic machine learning approach. And I don't know what is your intake of topic modeling using classic approach, but my personal intake is the topic modeling is very stubborn, was very stubborn. You could only go that far in topic modeling. You get some keywords, some terms from analyzing large amount of text data, but there's a lack of context usually, and you are not so sure about what topics are more important or prevalent than others. What are the stories behind those topics? So therefore, for a long time, I thought topic modeling was not a priority when you try to analyze text data and want to get some insights. But then the landscaping completely changed, and nowadays we have really capable large language models to help us decipher the topics in large volume of text. And topic modeling, I would say, revived itself to become important and prominent. So that's the reason why Charles wants to explore topic modeling and try to get some insights by analyzing text data. So without further ado, welcome, Charles. The floor is all yours.
All right, awesome. Thank you. Share my screen. All right, I'm guessing I could see on my end, so I'm guessing everyone could. Okay, so thank you, Professor An. So I'll firstly go quickly into topic modeling, how it can be applied to your research. I'll talk about traditional topic models. It's supposed to be LDA, not TopClus there. LDA, very briefly, and then I'll talk about LLM-powered topic models like BERTopic and TopClus, for example. So just very quickly, right? Topic modeling is when you have a collection of documents, text documents, right? And you want to get topics out of it, right? In the form of bulleted topics, right? So a good example is, for example, if I have all these documents here, right? Each are related to the causes of obesity, right? So you have drinking, you have exercise, sleep, pizza, right, which is eating unhealthy foods, right? You can kind of like sort it out into three topics, right? Number one is activity, right? Number two is diets, and number three is your lifestyle, right? So that's an example of topic modeling, where you have all these text documents and you try to put them into concise topics, right? Of course, here I use 9, but ideally you should have hundreds or if not thousands or even more of text documents when you try to do it, right? But just some notes about topic modeling. It firstly requires strong domain knowledge because as powerful as large language models can be, you still need to be able to understand, right, what the topic is saying and how it applies to your research question. And topic modeling is not summary. It can be used to achieve the same goals, but in essence, it's not summary. You're not asking a large language models to give you a shortened version of whatever you fed it in, right? You're asking it to give you topics, right? So which is why hence topic modeling, right? So examples of some topic models in public health and social work. I got this as the first one. I got this as recent as yesterday when one social work PhD student asked me, I have a bunch of notes. I just need to know what are the main topics of it. Can you tell me what to do? And my answer is topic modeling. And trust me, people have asked me this 5 times at least in the PhD suites. So hopefully don't get that again. You can understand topics from social media mining posts. right? Example topics like healthcare in America, for example, right? What are some of the topics that are constantly being brought up? You can try to understand prevalent issues in news coverage, which I'm actually going to show you later, right? If you have doctor's notes, for example, right, maybe you can extract issues and symptoms, right? But in essence, topic models don't have labels. That's when you use topic models. If you have labels, you should be using text classification, right? Topic models is an unsupervised form of machine learning, so you can't do it. So let me just quickly go through LDA topic modeling, which is a very classic topic modeling. And then from there, we'll discuss what are the problems. I ideally would not want to go through this, but unfortunately, because most of the problems are, that's how these LLM-based topic models try to be better, right? They try to look at the limitations of traditional models and try to compare them. So really, in essence, topic models, right, is when you have a bunch of documents. Each document is assigned a topic, and the topic is represented by words, right? So you can, so LDA stands for latent, I don't know how to pronounce this, the Dirichlet allocation. So the reason why I bolded the word Dirichlet, because it follows the, sorry, it's not. It follows the, Dirichlet distribution, right? Which is, you can basically think of it as a triangle, right? So in essence, for example, like the example I gave earlier, you have 3 topics: activity, lifestyle, and diet, right? So basically you're asking the model, hey, these are the 3 documents. Put them in this triangle for me, right? So, okay, you put them in here, right? The problem is, what if you also have something like beer, for example? Beer can be a diet, can also be a lifestyle. And this relates back to the original question, right? What causes obesity, right? Maybe you can put it somewhere in between lifestyle and diet, right? And then each of these topics can be represented by words, right? So for example, you have the word exercise, partying, drinking, food. So physical activity would be closer to exercise. Diets would be closer to food, can be close to drinking, but closer to food, right? Lifestyle, probably somewhere in between of partying and drinking, right? And just for information, this is done through Gibbs sampling, which is a Monte Carlo Markov chain method, right? For those of you who don't know, this LDA was made famous by Dr. Andrew Ng. Some of you know him from Costa Rica, but he was a Stanford professor in computer science before he went on to Costa Rica. So the problems with LDA is because they just use traditional machine learning tools, right? So you have polysemy and attention and long range dependencies, right? So polysemy, for example, let's say I gather 2 documents about Los Angeles, right? Let's go watch a LA Galaxy soccer game, and let's go learn about the galaxy in the Griffith Observatory, right? It's stubborn in the sense whereby it treats galaxy as the same, right? So, I mean, unless you want to play soccer in the galaxy, sure. But that's not the case, right? Because they use a bag of words format, right? So another issue is that words are dependent of each other, right? They have context, they're dependent of each other, right? So they have attention and long range dependency. So the first thing is, for example, low income communities are more prevalent to obesity due to the lack of investment in unhealthy food environments, right? There are some words that are more important to low income communities than others, right? So for example, the word dia, right, is referring to low income communities, right? And probably the word of lack of health investment in due to the lack of, sorry, it's actually the other way around. Lack of investment in healthy food environments. It should be healthy food environments, not unhealthy food environments. Healthy food environments, right, is also important to low income communities and should be given more attention, right? So that's when having pre-trained large language models can help, right? But there's also a problem, right? With just simply plug and chug. You can't just plug and chug pre-trained large language models into topic modeling. Firstly, you have the curse of dimensionality, right? Pre-trained LLMs are large in size. It's great, right? It can capture a lot of information, but now we end up with a lot of dimensions, right? The base BERT model has 768 dimensions, right? So that's not good, right? Especially if you want to perform unsupervised clustering, which is basically what topic models is, right? And the lack of contextual I'm sorry, I couldn't see my very own. The lack of good document representation, right? What I mean by this is, as I said earlier, right, many of these many of these large language models, they generate contextual representations, which means that they generate, a matrix, essentially a matrix, right, which has context embedded in it, right? So it represents context, not words. That's the very important thing, right? And the problem is that if you have topic modeling, you eventually want to map it back to words, right? Because topics are represented by words, right, from your documents. So you want to map it back, right? So you can perform unsupervised clustering on the dimensions itself as it is raw, but you will not be able to know exactly what the topic is about. You just know that this document is closer to than document A is close to document B, and it's far from document C. But what exactly does document A and B do, right? It's difficult to tell. And unsuitable PLMs, unsuitability of PLMs for clustering. This, I'm not going to go through the whole proof, but basically the authors of the TopClus paper prove that, right, because, so in essence, BERT-based models, they follow two objectives: mass language modeling and next sentence prediction, right? So let's just focus on mass language modeling for now, right? So you have original sentence: obesity can be caused by a lack of exercise, poor nutritional diets, and excessive drinking. The mass sentence would be blank can be caused by a lack of exercise, poor blank diets, and excessive drinking. The goal is that you're telling the BERT model, for example, right? Tell me what these masks are. So the masks are basically covered words. The model is not supposed to know it, and it's supposed to predict it. And that's how it learns context, right? So basically they prove that through this method of training, right, in essence, right, let's say you have V number of tokens in your BERT model, which is about 30,000, right? The optimal number of topics will just end up becoming close to, or if not equal to, the number of tokens that are available in your BERT model. Because in essence, when you do the mass language modeling task, right, you are covering some form of, topic allocation in that sense of a sentence. I know it's for those who are mathematically inclined, it's very difficult to understand right now, but you can go and read the proof in the paper. It's probably gonna take me a whole day to explain that. So yeah, so the first thing I'd like to present is BERTopic, right? And I'll go through each of these steps one at a time, right? So firstly, you have a collection of documents, right? You pass them into BERT, you get the contextual embedded representations, right? So far, so good. Anyone? So far, so good. All right. Right. And then now use UMap dimension.
So Charles, I want to pause a little bit here. I think probably not all of us may understand what Charles is talking about in terms of 768 dimensions. So basically, thinking about, we are representing each word with that many number of floating numbers, right? So think about each floating number is a number with decimal points, for example, 7.35, right? So that is a floating number. And then now we have 768, that many floating numbers as a vector to represent a token. So you can think of token as a word or a subword, right? So that is what Charles is talking about. Basically, when you apply the model, when I use the model as a giant mathematical formula, it's going to represent each token or each word in a sentence into that many dimension, right? Okay, so Charles, yeah, go ahead. Yeah.
All right.
So I just want to explain to those who might not be familiar with the large language model setup.
Got it. Yeah, thank you so much. So yeah, when you pass it through the BERT embeddings, you get contextually embedded representations, right? These already have context in them, so it understands the entire sentence, how it relates to each other, etc. Right? The problem is that they're very large, right? So we use UMap dimensionality reduction.
There's one question.
Yeah.
People may ask, why when you represent the tokens into a vector of 768 floating numbers, then there's contextual information embedded in that. Could you explain that in some detail?
Got it. So a very classical large language, a very classical word embedding, right? For example, you have the word queen and king, right? They could be very close to each other, right? But they are represented as individual words, right? When they're contextually represented, right, they take into account of the sentence as a whole. For example, like he is a king, right? And so instead of having just one matrix that is close to each other based on the words, for example, king and queen, right? They now have essentially something like a dense vector, which has incorporated everything that you have said throughout the whole sentence or throughout the whole whatever the window size is, throughout that whole window size, right? It's already contextually embedded inside that particular dense matrix. Does that make sense? Yeah. So
and for those who are familiar with the really simple correlation, right? So if you know how you are going to calculate correlation coefficient between two variables, right? So each variable is represented by a vector, right? So we have two vectors, right? And how you're going to calculate the similarity between those two words, then you calculate the correlation coefficient, right, between these two variables. Similar here, if you think, well, one token is represented by 768 dimensions, then we have two tokens. If we want to know how similar those two tokens are, and then we can calculate the correlation coefficient, right? So therefore, when the models are optimized for the embedding, then you could see that, for example, the king and the queens should have a very high correlation coefficient if you calculate that, right? So that is what Charles talked about similarity, right? Because you can calculate similarity between any two tokens in the embeddings. And ideally, when the models are trained, those tokens are close to each other, based on the similarity matter. Yeah, go ahead.
All right. Yeah, thank you so much. Yeah, that's a much better explanation. So in essence, right, you eventually have this 768 dimensions, right? And then, of course, across all the documents, then now it's too dense, right? So you use dimensionality reduction, and I'll visualize it as a dot here, right? You basically compress it into a dot. You compress all that information into a dot, right? And then now what you do is you perform HDB scan clustering, which I believe was covered in the machine learning class for those who took it. So basically it's a form of DB scan clustering, but the good point about it is that you do not need to specify the number of clusters. In some sense, it does it for you, right? Because it iteratively tries to expand the clusters and see how long it takes before they merge into one another. And because of that, right, based on that, it determines the optimal size or the optimal number of clusters that you're supposed to allocate it. And that's always has been a problem with classical topic modeling, right? Because in classical topic modeling, for those who have done LDA before, I think it's fair to say one of the most frustrating things is that you have to keep on running that over and over again. Let's try 3, okay, the words don't make sense. Let's try 5, it doesn't make sense. Let's try 10, 10 maybe it's a bit too large, right? But HDB scan, because BERTopic does HDB scan, right? It basically it decides the number of clusters for you, right? So now that we've clustered them, right, we need to map them back into topics, right? We know how many topics there are. For example, this one has 3, right? We need to map them back. So initially we have a collection of documents, right? And we know which document belongs to which dot at this point, right? Because we have traced them to now. So what BERTopic does is first it vectorizes the original documents, right? The words of the original documents. So you have all the words, word 1, word 2, right? And all the words here. You basically treat vectorization as a gathering of the words, right? And what it does is it uses a TF-IDF-like structure to gather the most frequent words associated with the topic cluster. For those who don't know TF-IDF, so it's basically like this, right? As you can see, W here represents how important a word is in this topic, right? And TF here, can you see my mouse? Yes. TF here represents how many times, right, this word has appeared in this cluster, right? So how many words? And the reason why you times this with the log of 1 plus A over TFT here, right, is because so A here is the number of words that appear in this cluster, and TF is the number of words that number of times this same word appears across all documents. But the reason why we want to do this is because words that appear frequently in this topic or clusters but are rare in other clusters, they are important. But words that appear frequently in this topic or cluster and are also frequent in other clusters, maybe not so important. Does anyone have any questions to now? I know I just went through a lot of math really fast, but
yeah, right. So for those of you say who are not familiar with the TF-IDF, I'll give you a simple example, right, to illustrate what Charles mentioned. So think about the word you, right, or the, or an, or a very common word, right, or I, right, because those words tend to show up on every single document. Then unfortunately you can't use those words to differentiate documents, right? Because those words appear in every document. Then those words probably don't matter that much, right? But if you want to differentiate between different documents, you need to look for the words that appear in one document but not in other documents, right? So that is the idea for the TF-IDF. We want to use the unique words appeared in a document but not in the others, then divided by the total number of common words in the documents, so that we can pay more attention to the unique words and pay less attention to the common words. Okay, so that is I would say a brilliant but also quite classical idea of how we differentiate different documents, how we pay attention to the uniqueness of one specific documents compared with the others. Yeah, go ahead, Charles.
all right, thank you so much. Yeah, just thank you so much, Professor An. But just to let everyone know, that's TF-IDF. Oops, why is this happening? That's TF-IDF, but what? I'm so sorry. I don't know why it keeps on lagging today. So yeah, but this time we are dealing with as a cluster. So we're not looking at document level, we're looking at cluster. So how many words does this, how many times does this word appear in this cluster? And we have clustered it contextually, right? Because we use the contextual BERT embeddings to cluster them. So quite a brilliant idea, right? So before I move on, let's start with a demo, right? So again, very easy, just pip install BERTopic. I decided to gather my data from news collector. So I tried to be as recent as possible as I could. So I collected the data yesterday. I'm not going to collect it in front of everyone because it's going to take a long time. But yeah,
so Charles, are you showing your a different screen, because we are still looking at your presentation? Yeah.
Thank you so much. Yep. Right. So yeah, again.
Okay, great.
This is how you install it. You pip install BERTopic. You install PyNews collector. I mean, you don't have to, but I'm just using it. I just use this to gather my data. I got it from news yesterday. So that's, hopefully we could look at more recent stuff and not something 5 years ago. Right. And then very simple, right? You just download it. Okay. So this is how my data looks like. I have titles, I have the articles, and I have keywords, and I have a source here, right? So let me just read my data. Okay, my data. So this is just the baseline, right? That means you're just performing with all the default parameters, right? You just use BERTopic and then you fit and transform your documents, right? As you can see, it produces rubbish, right? D2 in and D2 in off and D2 off end, right? Yeah, it produces rubbish. So what we do is that we choose n-gram range and we use stop words here. Basically, the idea being that we do not want to see all these, what I call rubbish words. We want to see meaningful words, right? So, and this happens, right? You just pass the conv vectorizer here as the vectorizer model. And essentially, right, what happens is that, right, when you're transforming back the words through TF-IDF, right, when you're transforming back the words, you ignore these these very trivial words, right? So let's see, and hopefully, okay, now more coherent topic models, right? Said year China, not really quite sure. Company growth year stock, right? Okay, makes sense, right? Something about company and growth. Something about cruises, I don't know, and something about the Kenyan economy, right? Again, we can see which document ends up in which topic, right? So for example, this is Bloomberg, so obviously makes sense, right? Company, they're talking about something about stocks, right? Here talking about stocks, and then we can try and understand what are the most persistent words, right, in each of these. So company, growth year, stock market, investor, share billion, Intel revenue, right? So it's better, but it's not the best, right? So let me go back to my PowerPoint and
so just one point that when you use the model, you've deleted the stop words, right?
so yeah, but the stop words deletion only takes into account when you're trying to map back the documents. So for example, you have this green cluster. You do not remove the stop words when you do not remove the stop words when you pass it through the BERT embeddings and cluster them, but you only do it when you try to trace back the words
to
the topic, to the clusters. Yes.
Yeah, so, and for those of you who are unfamiliar with the definition of stop words just basically means those words that are functionally important, but not really informative. For example, is, he, that, the, there. So those words are important grammatically because basically they are like the glues, gluing the context together, gluing the words together. But themselves, because they happen to be so prevalent across all the documents, so they are not really important, meaning-wise. Okay. Yeah.
Thank you, Professor An. Yeah. Yeah. So now, okay, it's not the best. It's good, but it's not the best, right? So what do? Well, we can fine tune them, right? So now that we trace back the words and we got the topics from the words from those topics, right? We can fine tune them, right? So, oops. Yeah, okay. So we were at this step, right, where we gathered the topics and the most frequent words associated with the topic cluster, right? So keybird, right, is basically the idea that you take the most frequent words associated with the topic cluster, right? You take the best represented document, right? That means the documents that best represents this cluster, right? So in this case, because this cluster is the furthest away from the rest of the clusters, you take this point here, right? And of course, this just assumes that two documents ended up in the topic, and I'm only classifying 4 documents, but please don't do this in real life, but just for demonstration, right? So you extract the most frequent words that appear and then documents that best represent the identified topic clusters, right? Again, you run it through the BERT model, right? So you run the document through the BERT model, and you run the word or the words through the BERT model, and then you try to compare and optimize. The idea being that if this was really your best represented document, and these were the words that represents the topic of the best represented document, they should be pretty close to each other, right? So that's kind of the idea. You compare and optimize, right? So again, the idea is to be as similar as possible. Questions? All right.
So I'm thinking about how you define the representative document. It seems like you could do something similar as clustering, and then you are trying to find the centroid of the cluster that could be representing the average, right? The average quoted, average document that could be representative. But no, so what is the technique, the exact technique involved in looking for identifying the most representative document, how they define it?
Okay. So during the cluster, right? Basically the centroid of the cluster.
Okay.
Yeah. Yeah, that's basically it. The one with the highest probability of belonging to that cluster.
Yeah, that makes sense. Yeah.
Yeah, absolutely correct. Yeah. But okay, so there's another one called maximal marginal relevance, right? And it's this equation here, but just let's ignore the equation for now. But for those who love math, that's the equation right now. So the idea being that the most frequent words, okay, again, most frequent words associated with this topic cluster, right? Going outdoors and outside, right? Assuming this is your output of your topic model, right? Fine, right? You know, it's great, but outdoors and outside is the same, right? Why are you giving me both the same words, right? It's no thank you, right? So you select the most identical words with respect to the topic. The idea being that because it's so similar to each other, right? This is where DI and DJ comes, right? Right. It eventually has such a low marginal maximal revenue score, you basically throw away the word, right? Because it clogs up the outputs. You throw away one of the words, right? So now outside is thrown away. And then now, for example, the word exercise would come in. So going outdoors to exercise, that sounds a lot better, right? Because now you have eliminated words that sure, outdoors and outside appears very frequently and they are part of your topic, but because outdoors and outside is conveying the same topic or conveying the same idea, you do not want that, right? So you get rid of one and now you have a more synchronized or more understandable output, right? Going outdoors, outside. So that's MMR. And there's also one is zero-shot classification, right? So sometimes, but the problem with zero-shot classification is that you need to have an idea of what your topics are already representing. So let me just go through that, okay? So sometimes when you look at the labels, right? Okay, so for example, you saw it, okay, oh, okay, I may have an idea of how this topic is like. For example, this is physical activity, for example, right? And the words are not very helpful. You want them to generate more representative keywords, right? So, oops. So you tell the large language model, right? This looks like physical activity to me, right? And what it does is that it performs zero-shot classification, and then it generates more coherent topics like run, jog, brisk walk, and outdoor, right? So it eventually gives you more relevant key terms, right? So yeah, again, sorry, my bad. Okay, so what I meant to say was, okay, if you had a document with run, jog, brisk walk, and outdoor, you tell the large language model, this looks like a physical activity to me, right? So it performs zero-shot classification assignment of labels to the topic, and it gives you outdoor and physical exercise, right? Much better than just a bunch of actual physical exercises. It, classifies them together, right? But this assumes that you know that this is physical activity, right? So you must tell the large language model, it looks like physical activity to me.
Yeah, so one comment here for those who are unfamiliar with zero shot, basically it means when we use large language models, we have a few choices. Zero shot means that you do nothing to change the model architecture or ways, you just use the model as it is without providing any examples. So here, Charles just provide the topics, right? The run, jog, brisk walk, and outdoor. He doesn't really provide any example. He just provide a topic for the LLM to classify. So that is called zero shot. In comparison to few shots means that you provide a few examples. For example, here Charles may mention this topic 1 belongs to physical activity, and maybe with topic 2, including maybe birthday cake, pizza, Coke, and then that would be diet, right? So if Charles provides some labels denoting what the topic is, then Charles is doing few shots classification. Okay, so that is the definition for zero-shot classification. So basically, what Charles do here is utilizing an existing large language model to try to make sense of the topics based on the keywords.
All right, yeah, thank you, Professor An. Any other questions from anyone else? I know.
I have a quick question.
Yeah, go on.
As to the zero shot and a few shots, as to the few shots, if you give some examples to the model, then does this process is doing a fine tuning?
Oh, no. It's different from fine tuning. Fine tuning is that you have a very large language model, right? And then you're giving a lot of examples to the large language model, labeled data, and you're tuning the parameters of the large language model. So it's like, you have a large language model, right? It has already numbers inside, right? Weights inside, right? And then you're tuning the numbers, right, inside the weights to make it fit to your case. So you can think of parameters as like like a linear regression, for example, right? Classic linear regression. So for example, you have your intercept, and then you have your what's that called? The dependent variable. I'm sorry. Dependent variable, the independent variable.
The coefficients. Yeah.
Coefficient.
So,
yes, coefficient.
Yeah. Or
Thank
the
you.
intercept
Yes.
and slopes. Yeah.
Yes, coefficient, right? So it's fixed, right? So zero shot is like, okay, input, output, right? Using your existing coefficients, right? Right. You can't really do few shot, but fine tuning would be when you have new examples and then you feed it in. Think of it as a doorknob. So you're trying to just twist about the coefficients, adjust it here and there such that it could fit your new inputs with your outputs perfectly. Did I explain it correctly? Well, yeah. So fine tuning is, when you have the whole large language model, and then with all these parameters here, and you're trying to really just like adjust the numbers of these parameters such that it could fit well and adapt to the data the new data you're providing it with, which is never seen before. Yeah.
Okay. Thank you so much.
Anyone else? All right. If not, then I'm just gonna go on with the demo. Again, please feel free to interrupt because I know I've went through a lot of math in a very short period of time. So first we're doing maximum marginal relevance, right? So again, you can define the diversity here. The idea being that, how diverse, basically how much of that similarity do you want to eliminate, right? So a more diverse model will have very strict, if it's remotely similar, it will just eliminate intercepting keywords, right? So, okay, for some reason now this backfired because for some reason cookies ended up here, but probably Taiwan, oil, and global. And the representative document kind of makes sense, right? Because this was new script yesterday, by the way. So for those of you who don't know, they recently had an election there. So makes sense, right? As somebody who knows what's going on. Billion Kenyan market government, right? So probably talking about the Kenyan economy, not really quite sure. Companies, investor, Intel 2023, right? And then again, right, this is probably talking about stock news, right? Your typical stock news for the day. So again, we can see, okay, billion Kenyan market government company says bond bank sector. So something about the Kenyan economy, right? And again, we could run the model and we could see where ends up where. I mean, I'm not sure why cookies keep on appearing here, but sure, right? Makes sense, right? With regards to well, I mean, not really. It's classifying the wrong type of country, but anyways. And then, okay, this makes more sense, right? And Intel stock fell more than 10%, right? And of course, right, company investors, Intel 2023. Again, Intel tumbled, so I'm guessing, so you can see now, right? Okay, fine, yesterday there was some major slump from Intel and all the newses are reporting about it. And here you actually could even output the probability that this particular topic belongs to this particular article in my case, right? So it's pretty high, right? It makes sense, right? Because, okay, now that's not, okay, here's talking about the Dow again, right? So definitely belongs to the same topic. Here is a bit less confident, right? Because it gives Intel, but it's talking about Boeing, but nonetheless, probably still talking about stocks, right? So yeah, much more coherent, right? Compared to the previous one that I showed you. Now let's try keybert. Okay, and we get something different actually, right? Demand, CEO, market rents, not really quite sure. All right, this is better, right? Kenyan, Nairobi, and bank finds, right? Stocks, stock dividend investing, right? So again, we can check it out, right? Something about regulations, right, of the Kenyan government, Federal Reserve, or the bank, or whatever you want to call it, right? And then again, right, you could do it with again, right, you could inspect the probabilities of each word belonging to each topic itself, right? One thing to note is that keybert gives much higher probabilities for the keywords belonging to that document, because like I said, again, we iteratively take out representative documents, a subset of the documents, and we iteratively take out words, right? So obviously, naturally, you would get a higher probability. So yeah, there's that. All right. I think I have zero shot, but somewhere else. Yeah, I think zero shot is somewhere else. Okay, I'll show you probably later. So now the question is, can I use a different model, right? I don't like BERT, but it's old-fashioned. It's 2019. Can I use something else? Yes, you can, right? You just have to specify embedding model, right? And then just feed it in here and you run it. And then, yeah, much better now, right? Something about rents, right? Stocks. Okay, now there's environment, right? EP environment, and then about again, right? The Kenyan bank. I don't know what happened in the Kenyan bank yesterday. Should have checked it out, but I don't know. Okay. So anyways, yeah, so yeah, again, right? The same thing again, you can obtain the topics, right? And now the order got swapped. But yeah, you get stocks, dividend investors, shares, market earnings, and financial markets. Now we're going to try long former. And the reason why I use long former is because it's suggested, right, basically to use a large language model that could interpret long-term dependencies, long-term context within each other. And that's exactly what long former does. So let's give it a try. Much better now, right? You see, energy, transition, climate, right? Artificial intelligence, 15 billion. Okay, something about artificial intelligence making massive gains, right? Transport board, long-term investment, right? Something about, see, well, my guess is that if you've been reading the news, I guess it's probably about Boeing 737s blowing up in the middle of the air. But yeah, that's probably what it is, right? And then again, something about pollution in the EU, right? Again, about stocks. And for some reason, something about the Kenyan economy. Nairobi collects more than, yeah, something about the Kenyan economy, right? Again, you could run it and then you could see the individual keywords associated with it, right? So using long former, from what I experienced so far, is the best because it could really capture the long-term dependencies. And it shows, right? Because you see, look, energy transition, climate change, geopolitical. For some reason, there's Getty images here. Reality Labs. Okay, and the rest are probably a bit of rubbish, but yeah, it's basically it. Any thoughts? Any questions?
I have a quick question.
Yeah, go on.
About the long former. So, does that mean involved more tokens during your calculation in your model when you processing the data?
Not necessarily. Basically what happens is that, you know, in the classical BERT, I think it's 512 tokens that in which is limited to, the window is limited. So for example, if you have an article of 5,000 tokens, for example, right? It could only understand the context, maximum context of which of 512 tokens. And after that, it has to keep on, you know, it doesn't go beyond that, right? Long former is able to capture much longer token range, right? And this token range is important to understanding context, and which is why it performs much better in ours, because we are using newspaper articles, which I'm sure it's more than 512 tokens. So therefore, BERT was not able to capture, it's able to capture context, but in such a very short term, it's just limited to 512. So Longformer is revolutionary in a sense. It's now able to capture much longer dependencies, much more than 512. I don't remember the exact number, but if somebody remembers, maybe they could help me out there. Yeah.
I think you're right. I think you're right. The Longformer takes 4,096 tokens as the window size. We call it the maximum token size. Basically, you could think of, if you want to bite a burger, the size of your mouth is the max number of tokens, right? Because you can only bite that much, and you have to consume the burger in several bites, right? Unless you are a eating champion that you can eat a burger in one bite. Usually we spend, I don't know, 10, 20 bites, right? So one bite is the one maximum number of tokens for the models. Is the model, what we call it, window size. Okay, so because it has been the small of the window size is almost always a problem for large language model until really recently that we see Cloudly allow you to have a maximum window size of 200,000. And ChatGPT, GPT-4 model recently released the GPT-4 preview 1106 version that allow you to put 128,000, I guess, right? So until recently, it became less of a problem for the window size. But for traditional, much smaller language models, the window size is a big concern because the model can't really consume larger than that text data. So you have to feed the data iteratively to the model. So that is what Charles mentioned about the difference between long form and the BERT model, because BERT model can only consume 512 tokens, okay, much smaller in size. Yeah, go ahead, Charles.
All right, thank you so much. Right. So the good thing about BERTopic is that really, right, it accommodates to different scenarios. So I'm gonna go through the different scenarios, and then I'm gonna demonstrate them to you, right? So the first one, I'm not sure why I did that. Gosh. I'm so sorry. I'm not sure why I did that. Really so sorry. Okay, so the first one is supervised, right? Very easy, right? I have data, I have my labels, but I do not know, I want to know what's inside the labels, right? I want to know what words are prevalent in the labels, right? So how it works is that they just very simple. They skip UMap and DBScan, and they immediately insert in logistic regression as a classifier, right? And then from there, it's very simple, the same, right? You count vectorizer, TF, IDF, and then fine tuning, right? Semi-supervised, what if I have my data, which is partially labeled? I already have some topics that I have identified, but I do not know others. So it's very simple. You just insert your labels during the dimensionality reduction step, right? It nudges the remaining unlabeled points based on the labels you provided and the examples you provided, right? And it clusters them accordingly, right? And I'll show an example later. So manual, this is very confusing, I know, but what if my data is already labeled with topics and I want to just have a better understanding of each topic, right? I just want to know what keywords are associated with topics, right? So you just skip the entire, it's basically not even, there's nothing involved at this point, right? You're just inserting your documents and labels and they're performing TF, IDF for you. The difference between this and supervised is that supervised, you are building a model, right? You're building a model. So the difference between this and supervised is that you're building a model, right? You're still embedding the text and whatever, but you're building a model to basically understand the outputs. This one, you're just purely trying to infer. You're not building any model or any predictive model, right? And this is the best thing I like about BERTopic is dynamic topic models, because in reality, right, you want to see how your topics have changed over time. And later, I'm going to show a really good example I'm going to show tweets from COVID-19, and I'll show you how the topics have changed over time. And this is very useful for researchers who, for example, you do sentiment analysis, right? Maybe in your next sentiment analysis paper, you could run a dynamic topic model to try and see how has the topics changed over time, right? So this is very useful, and I absolutely love this, right? So how it works is that, again, embeddings, dimensionality reduction, clustering, right? So now it performs the clustering within each cluster, right? So again, it clusters all the documents together. So it does not cluster at each time step. It clusters it in all together. It has these clusters, right? And then, never mind, forget it. Okay, and then it divides them based on the time step, right? So you have time step 1 all the way to time step m within each cluster. So now it has a cluster. It just divides them, partitions them based on the time step, and then it performs the TF-IDF. So it only identifies the prevalent keywords within that time step itself, right? But the important thing is that it was clustered all together, right? Which topic it belongs to is clustered all together. The logic for this being that, right, at the end of the day, right, indeed, it will not, it will be a bit too fine-grained, right? If you were to split into timestamps and then cluster it, you want to get the whole big picture of it. So this is why they do it. And hierarchical clustering modeling. So sometimes, for example, and later I'll show you another good example, they would produce 100 topics, for example, right? Okay, fine, that's 100 is great, but it's a bit useless, right? Why want 100 topics, right? But sometimes if you look at the topics, and you could have seen just now earlier, right? They were talking about the stock market, and they were talking about the Kenyan economy, right? In some sense, you could say both of them are subsets of each, both of them are subsets of a greater topic. And this is when hierarchical topic modeling comes in, right? It's useful when, it produces, let's say, 10 topics, right? But 3 of the topics are related to each other, and they could form a bigger picture. This is when hierarchical modeling, topic modeling comes in. So how it works is that once it produces the TFI, basically your representations, the TF-IDF, right? It calculates the cosine similarity between the topics, right? And it applies a linkage function, right? I think it uses Ward linkage. So it applies linkage functions, right, to group the words, the keywords of each topic that have already been discovered. It groups them together, and then it updates the TF-IDF representation of each of these documents, right? And yep, okay, there's that. And I would now show you, I think I should have all of them. Okay, I'll now show you all of it, right? Let me just want to shut this down. Okay. Again, data with topics, right?
Oh,
So
Charles, we are still looking at your presentation.
Oh, I'm sorry. Thank you so much. Yeah. All right, cool. Awesome.
Yeah.
Right. All right. Awesome. Yeah. So again, same, you import everything, just read the same thing. So this time what I did, because I want to show supervised, so I'm the sole labeler of this, so don't blame me for this, but I just manually labeled it based on what I saw. So forgive me if it's bad, but I'm just trying to show how supervised works, right? So again, I labeled them into economy, election, environment, Israel conflict, and others, right? And again, I showed you earlier that if you have the labels, you can make a predictive model through supervised learning, right? And then it's very simple. All you have to do is that you have to map it back. I really have to caution you that if you do this, right, do not use label mapping, your initial mapping, to map it back to the BERT topic. And I'll show you why, right? Because if you look at mapping, for some reason, BERTopic likes to mix up all the numbers. So what was previously 1 is now, or what was previously 0 is now 1, what was previously 2 is now 4, and everything like that. So please be very careful when doing with that. Okay, so what do we get, right? So like I said, this is 5. So okay, economy market investment financial securities, right? Let's take a look at it. Okay, so market investment securities, market intel economy, intels, right? So something probably about Intel, right? Okay, Nairobi, Kenya, I don't know what. Okay, so let's just take a look at this. The first one, okay, again, something about the Kenyan economy. I wish I read more, but I don't know, right? Right, the third one is about the environment. Again, these topics have been manually labeled by me. So they, they are, obviously they make more coherent sense, right? And then the third one would be the Israeli conflict, right? Makes sense, makes a lot of sense, right? And then again, right, the election, right? And for those of you who don't know, there's an election going on, I guess. So, New Hampshire, which I think was where it was held, right? Republican, non-incumbent Republican win. For those of you who understand what's going on, should be pretty easy to understand what's going on, right? That the that the incumbent won, right? So, yeah, that's basically it. So now we move on to manual topic modeling, which, like I said again, you're not building a predictive model. You are just classifying, right? I'm just trying to understand which words are prevalent in each already labeled topic, right? So to do that, okay, actually I forgot to mention, right? When you do this, right, you have to really specify that you want an empty. The way you do this is that you specify that I want an empty dimensionality reduction model. You specify which classifier to use, and then yeah, so you basically actually have to do it manually, which is why, as much as I don't like it, I had to go through each and every single step, because that's how BERTopic works, is that it expects you to, it's not just, hey, this is supervised, you have to specify the parameters yourself to know it, right? So in this case, I tell the model, we have no dimensionality reduction because it's supervised, right? Instead of having a clustering method, we use a classification method, right? And therefore we feed it in. And the same for that, right? We have no clustering method at all. We have no embedding at all. We're not embedding anything at all, right? So we just give a base empty. We give it to them as an empty step, right? And then again, okay. So Intel's year set market, okay. I do not know what was this, Taiwan? Yeah, again, coffee gas. Okay, fine. The Israeli conflict makes sense. The fourth topic makes sense. Okay, actually, no, this is better, right? The fourth topic makes sense, right? Election, this one makes more sense. I'm not sure how coffee comes into environment, but and then the others, I'm not really sure about this. And then the economy, right? So I guess we can all tell that it's time to buy Intel stocks, right? Because it keeps on showing up. But yeah, that's that. All right. And then again, semi-supervised. So basically what I'm going to do now is I'm just going to insert whatever so I previously showed you that I labeled by myself very poorly, but I labeled some of these articles. Now I'm just going to insert the unlabeled ones back in, right? And then I'm going to just run it again, right? And the way you do it is that for those that are not labeled, you just simply insert -1 inside, right? And yeah, okay, not really the best. What it mostly does is it tells me that -1 is -1 is investor stock, and then this one, I mean, it's almost the same as 0, so not very helpful. Yeah, again, right? And now this is when zero-shot topic modeling, which I missed out earlier, comes into play, right? So like I said, okay, from everything that we have gathered so far, I could tell, it's economics. Actually, I should say economy. Economy, election, environment, Israeli conflict, others, right? So let's put it and let's tell the large language model to help me give more coherent sentence outputs based on that. So we can elaborate the minimum topic size that we want to consider and the zero-shot similarity, right? So the similarity between the topic that I'm providing here right? And the keywords in itself. So let's see. Much better, right? Climate change, energy related supply. Let's do a bit. Let's do this, right? Let's see the first topic. Okay, great. Artificial intelligence, 15 billion, fourth quarter, data center, dealership, economy. Okay, this from here is rubbish already, but you can kind of see, right? It's something about artificial intelligence, great fourth quarter earnings. It's, you know, the future economy, right? The next one, right, is I guess it's okay. Yeah, it probably got mixed up. All right. Tax incentives, exemption, right? Union workforce, emerging markets, incentives, right? This is the economy. All right, and this is environment, right? Spokesperson, pollution, something about in Euro, in London, and parking cost, right? Which was what I provided earlier. Okay, environment. This is probably others. I don't know. Let's see. Right, this is yeah, this is probably others. I'm got it mixed up somewhere. Okay, never mind. But yeah, you basically get the point, right? It tries to give more coherent outputs based on what you think are the topics that are already existent within your outputs itself, from your outputs based on what you inferred. Any questions?
Yeah, any questions from the audience? Anything you want further explanation by Charles or by myself?
I have a question.
Yeah, go on.
As to the topic, at the end of this file, you tabbed it. Is this represents many articles, or is only one article?
Oh, you mean this one?
Yeah.
Oh, so these are the topics generated. So for example, this first topic is about climate change, right? So I want to see, they provide it here, right? Climate change, energy related supply disruption. So, I mean, it's just a, okay. Which is which? Okay, got confused. All right, let's not use this. I forgot to map it back, which is why it's very important, right? I missed it out on the last step. It's very important to map it back because BERTopic likes to mess up all the allocations that you provided to them. So, okay, but let's look at this one, for example. Markets, financial incentive securities, right? So markets, investment, it's basically the same. You see? So here's markets, investment, financial securities. It's all the same. It's just providing the probabilities of the keywords for each topic that it identified.
I see. So the count here means the number of articles?
Oh, you mean count here, is it?
Yeah.
Yes, that's correct. Yes, that's correct.
Oh, I see.
30 articles have been classified into this topic cluster, 17 into this, 6 into this, 2 into this, and 1 into this.
And the out here represents the possibility of the most relevant topic it calculated.
Which one? This one or?
Yeah, I mean the out. The
This-
output, yeah.
Oh yes. No, these are the probabilities that the words belong to this particular topic.
Okay, so the toppest one is the one like the model recommend.
That's correct. So this is, well, I mean, let me correct myself. I said it wrongly. This is the highest TF-IDF score. So earlier I showed you the TF-IDF score where it tries to identify how each cluster has the most frequent words relative to other clusters. That this is the TF-IDF score here.
Okay, I see. Thank you so much.
Yeah, sure. Thank you for the great question.
Well, I have a question about the TF-IDF score. Does it have a range? It's from 0 to 1?
Does it have a range? Is it from 0 to 1? It's a good question. Does it have a range from 0 to 1? The answer is I don't recall. I should know this by now.
Yeah, no, the TF-IDF actually is a suite of matters, really depending on which specific TF-IDF is implemented, because there are several different or relevant definitions. But for this one, I think so. I think it should be ranged from 0 to 1. Most likely it has been normalized, even if the traditional TF-IDF doesn't have to range from 0 to 1. They have been normalized to this range in the implementation. So I think that's the case, but we have to double check the documentation to know for sure. Yeah.
Okay, I see. So we just need to know which one is the highest, but we don't need to know what, like, from, like, how large this number should be to be important, that word.
Yes, that is correct. So for
Oh,
example,
okay.
here it's 0.45, right? And then if you scroll all the way to the bottom, it gives like a 0.90, right? So it depends, right?
Yeah.
So
Okay.
there's probably no consensus regarding the threshold for TF-IDF. It's in relative terms. Yeah.
I have another question about the zero-shot classification at the end. I was curious. So for the zero-shot, we define all the topics names.
Oh, okay. So
for
example, yeah, great question. So for example, right, I have read some of these outputs, for example, right?
Yeah.
So I read some of these outputs and I think, oh, okay, maybe this is the economy, right? This is the Israel conflict, right? This is the election, right? So I'm just telling the model, hey, I think these are some of the topics, right? Can you help me give me better outputs based on what I think are the topics, right? So it then gives me, as you can see, I gave one on the environment. It gives a much better one, right? Climate change, energy-related supply disruptions, right? It gives me much better outputs now, much more coherent outputs, because you told the model, I think these are some topics that I have. Can you please help me rearrange the words such that I get such a smoother, much smoother one? And then I gave one for the economy, for example, and then they talk about artificial intelligence. Where is it? Artificial intelligence, 15 billion fourth quarter, right? And he gave another one about tax incentive exemptions, union workforce, emerging markets, right? So it's able to go through your topics and go through your keywords and give better outputs, for example.
Okay, gotcha. Thank you.
Yeah, I have a question about can you go back to the time, like the PowerPoint about clustering using the
time dynamic,
to the
right?
time series, the timeline, like
this one?
I can see.
Oh, I'm sorry. I'm so sorry. Is this it?
Yes, dynamic. So you said you can input all of the data setting into the model and then do the clustering. Then how to do the time series analysis?
Okay, I'm just about to show that. So just hold on for 2 minutes. All right. Just hold on for 2 minutes. I'm literally about to show that. But thank you for queuing me in. I will show you how it works. Yeah, I think I've done it here. Visualize topics. Good. Yes, topics over time. Okay, I'm about to show you. All right, so hold on. All right. So now, so far I've dealt with, let me just restart this. All right, so far I have dealt with news articles. From now on, I'm just going to deal with tweets. I got a COVID-19 tweets data set. And we're just going to sample 10,000 out of it just to save everyone's time. So here we just perform a bit of cleaning, right? And then we, okay, great. It's such a large data set, it takes time to read. So yeah, okay, just, I'm sorry, everyone, you have to wait for 1 minute. Yeah. So basically, we do the same, right? Vectorized model, TF-IDF, we tune it with representation model. Again, right? So to answer your question, Yui, we basically cluster all the documents together. So as you can see, I have these tweets here. I'm just clustering all of them together. Only after I cluster them, then I would visualize them over time. All right. Then I would visualize them, how it changes over time. And you're about to see, because they have a really good visualization, which I would highly recommend. But let's just wait. Yeah.
So here, just want to add that if you want to do this type of modeling, making sure that all the twists belong to the same topic. Otherwise, you are mixing up. Though because what Charles demonstrate here, because all the twists are related to COVID-19, so that's okay, right? But if you think there are a lot of topics there, then you have to classify them into different topics, and then do the hierarchical analysis or time series analysis for each topic separately. Otherwise, you are mixing the trends with different topics.
Makes sense.
So we're just running this. All right. And there is something called, let's just wait. I'm sorry, everyone. All right, but there's something called LDA Vis, which is very popular in classical LDA, right? Such that if you have a lot of topics, right, and you want to know how do they look like in a two-dimensional space, right? How similar they are in a two-dimensional space, you can use visualize topics here to visualize them. And you would see it in, yes, okay, great. So for example, here, I have 124 topics, not very helpful, right? So I could actually go in here and see which topics are very similar to each other. And it makes sense, right? So for example, oops, you see, nurse, night guild, nursing student, right? Something about COVID-19 and nursing. And then here is about hospitals, hospitalization, patients, coronavirus in Philadelphia, right? So you can see, right, it does a pretty good job in clustering the topics itself. Let's select another one. Social distancing, and what's the other one? So, okay, social security. Okay, both social distancing. I don't know why social security turned up there.
Do you know the x-axis and y-axis mean?
So yes, okay. So you can think of it as like principal component analysis, right? You have many components, but you only analyze them on a two-dimensional, in two axes, basically. So this is exactly like principal component analysis. It's just visualizing everything in 2 dimensions. And you could even drag to see where each topic belongs, right? So pretty cool. And this is what I'm very amazed about. You can see, right, how the topics have changed over time. So this is March the 9th. Let's see. Okay, for those of you who remember, not that I want to, coronavirus, right? Italy was one of the countries to first have it, right? So Italy tweets were the most famous, right? By the March 13th, okay, people were talking about, okay, the apocalypse, right? It was going to happen, right? And people were upset that sports was cancelled. So that's another topic, right? And apocalypse, right? Maybe go somewhere here. Okay, maybe same coronavirus. And then people started March 17, right? That's when people started talking about what's that called? Essential workers? Is that what you call them? Essential workers, right? Is that, yeah, essential workers, right? About safety of essential workers, basically, right? And of course, that's when this, okay, that's the blue one. So then you can see, right, somewhere mid-March or towards the end of March is when really, right, the anti-Chinese or the anti-Asian hate started to come because of the COVID-19 pandemic, right? And you can see now it's starting to peak, right? And then after that, people started getting concerned. How am I going to go to the supermarket, right? Because of COVID-19. And then New York. And what's this here? Just out of curiosity. Okay, Maryland, Illinois, never mind. Yeah, but basically you see, right? Is I don't know. I don't know about you, but I think it's pretty awesome, right? It's you can see how each trend changes over time, right? So
Yes.
yeah.
If you change the top end topics to like 5, would
Yeah.
it clear?
Yeah, I would agree. No, I would change the topic to 1 so that we will see just the most prevalent topic at each time point.
Oh no, I think if you change it to 1, it's just gonna produce 1 topic only.
Oh, really?
Yeah. So
okay.
Yeah. So it's recommended that, for example, if you have at least the document recommended, for example, if you have 30 times time points, you make it 30. So
It's the frequency. Okay.
Yeah. So
Okay, I see. Yeah, that makes sense. Okay, I was thinking of okay, so it's different. Okay, it's the transition of topic, it's transition of frequency. Okay.
Yeah,
that makes sense. Okay.
Yeah. And again, right? So again, here we have 124 topics, and then we have hierarchical topics. So again, right? How can we visualize them? Okay. And then you can see, right? So here it's about patients and clinicians, COVID-19. Is that where I can zoom? Okay. Not very nice. No. Okay. Never mind. Okay. So here it's something about patients and I don't know. Okay, let's use something more. Okay, there we have it. Okay, I'm sorry. Something about curfew, coronavirus, lockdown, and coronavirus. Okay, here's a good one. Celebrities, celebs, right? Coronavirus, Tom Hanks, for example. So we know this is about celebrities, right? So we can merge them into 1 grand topic here. And all these also could be merged, right, into existing topics, right, up to the point where you basically get 1 topic here as a whole, right? So this is how the hierarchical visualization works, right? You basically have so many topics, but you know that there are subsets of each other, right? So here's another good example. Senate bill, Senate Congress, right? Coronavirus Democrats, right? Probably referring to the same thing, right? I don't know, why is it? Oh, Pelosi. Okay, Pelosi. I thought it was Pepsi. Pelosi, right? So probably all belong to the same thing. So it can be all essentially grouped together in a hierarchical form, right? And you could from there here, okay, Pelosi, Senate bill, stimulus, Kennedy's, Democrats hate America. Okay, yeah, but basically the idea being that, okay, this is something about politics and the stimulus bill, right? And yeah. So, and the same thing here, right? Oh, this is another good example, the yellow ones. Healthcare professionals, healthcare workers, right? Yeah, sure. They're a bit too similar to each other. So they're here talking about healthcare. You see, by the time you merge, it becomes, right, healthcare professionals and patients and, right, something about curfew related to them. I don't know, right? Yeah, so this is a really good example. And another thing is that you could also do topic distribution, right? Okay, topic distribution is not defined. Okay, I may have, never mind. All right. I was hoping to show, yeah, I may have actually deleted something here, but what I was supposed to show is that if you had, for example, labels, you can visualize, right, how they look across different labels. But yeah, I must have done something wrong here, but apologies for that. But yeah, yeah, basically that's that. Okay, I'm aware it's 8:30 now. Unfortunately, I'm probably going to take much longer than 8:30 to move on to my next part, which is a different algorithm. So I don't know.
I think
verdict?
no, just for the time's sake, we are passing the 1.5 hour time mark. So maybe we should stop here and ask whether any of our audience have any questions for Charles. I think it's a fantastic talk. Really, I don't know much about the most recent development in topic modeling I think it's tremendously helpful, especially after the modeling incorporate large language models. So any questions from the audience, any pressing questions, anything confusing, just unmute yourself and ask.
Unfortunately, I have another 40 slides, so I don't think we're going to finish it.
Yeah, we'll see for the next time. No,
Yeah,
we'll probably revisit this topic. So what I want to say is, we have for those of you who have something else to do, feel free to go. I just want to briefly comment a few things. Maybe using a few minutes. I'm thinking first, the topic modeling is revived because of the large language models. And as Charles mentioned, there are now a lot of different time series analysis, hierarchical modeling. Those are really new to most of us. And second, I do hope that maybe Charles, maybe Yu, and probably many of you thinking about how we can push the envelope. So, one thing that really, I'm really struggled is we have to basically guess the meaning out of many keywords, right? And the keywords are not really consistent. We are half guessing and probably half just imagining what could be the case, right? So could we do a better job in terms of providing, say, a brief summary, like a one-sentence summary of the document so we can understand this better, or one paragraph description of the topic, right? So we understand the topic better. I think we can definitely push the envelope in multiple directions. One is to think about how we could use, say, large language models. Maybe we can do a document by document, one sentence description, summarization, and then based upon that, we can combine the documents together or can compare the similarities and cluster those documents into different types. Presumably, I think this approach would be more robust compared to using keywords, the TF-IDF, which we know doesn't really consider the meaning, but merely is a bag of word kind of approach, right? So another thing we could do, I'm guessing, is to embed the large language models in other domains, for example, summarizing the topic in a paragraph or a sentence, so we get more contextual information out of it. Regarding time series analysis, we could probably describe the trend over time, using sentences or paragraphs. Basically, we could think about multiple ways we can reorganize the workflow, the pipeline, so that we can get more from mere keywords and broken sentences, right? We is of course computationally heavier and need some innovations, but I think we are in a good shape to renovate this idea and probably push the boundary of this topic modeling. So yeah, so Charles, if you have time later on, we can discuss, maybe even write a paper on how we are going to renovate this kind of pipeline. So there are multiple dimensions we would go with. We'll compare the pros and cons. And for the rest of you, I would urge you to think about what are the limitations. Now the topic modeling is much better, compared to before, but what the limitations you see and how we can better address them, right? To push the envelope, to move the topic modeling to a new domain, I would say, that is making it more accessible, understandable, and giving you more insights. Okay, so that's my 2 cents, and thank you, Charles, for offering this very intensive and informative talk. I know, you always go ambitious, you want to cover everything, but I think we already received a full dose from you today. And definitely we will seek other opportunities to revisit this topic, maybe starting with what you left today, and maybe even moving to reviving this pipeline so we can push the boundary a little bit further. Okay, so that's all I want to say. And thank you, Charles, and thank you everyone for coming. And we will see each other in 2 weeks, right? So we will not meet next week. We will meet 1 week later. So at that time, in 2 weeks, Yu is going to give us a presentation about fine-tuning, how we can fine-tune huge language models. For example, the GPT models, and maybe Cloudy models, Llama 2 models. Now we have a lot of ways actually that greatly simplify the fine-tuning exercise using Google Cloud and Azure Cloud, etc. Okay, so we'll spend the next talk around fine-tuning large language models. Okay, so everyone have a great weekend. We will see you in 2 weeks. Bye.
Bye. Thank you, everyone.